This is the 6th how-to tutorial for Chem 1011, and in this tutorial we're going to talk about 3 rules that we talk about when describing atomic structure. There's the Aufbau Principle, Hunds Rule, and the Pauli Exclusion Principle. We'll start with Hunds Rule. And Hunds Rule states that when filling a degenerate set of orbitals in the ground state, pairing of electrons cannot begin until each orbital in the set contains 1 electron. Electrons singly occupying orbitals in a degenerate set have parallel spins. In this case here, notice that we only have the 2 electrons. They have parallel spins. In other words, this one here or this one here, they're both pointing in the same direction. That's what we call parallel spins. In this case here, this one's pointing up, this one's pointing down. Okay, so they have non-parallel spins. In this case here, the 2 electrons have been placed in the same orbital. This disobeys Hunds' rule. The Pauli Exclusion Principle was named after Wolfgang Pauli, who got the Nobel Prize in 1945 for his work in this area. The Exclusion Principle states that no 2 electrons in an atom can have the same 4 quantum numbers, N, L, Ml, and Ms. This means that every electron in an atom is uniquely defined by its set of 4 quantum numbers. No electron can have the same 4 values for these 4 quantum numbers. In the incorrect example here, these 2 electrons, they have the same values for N, L, and Ml, but their spins are parallel. They have the same value for Ms, in this case plus half. This is incorrect. In the correct example, notice that not only N, L, and Ml have the same values, but also Ms and for the 2 electrons have opposite values, which is the exclusion principle obeying itself. So in this case, this is correct. If we look at a small handful of examples, in this first electronic configuration, we have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then there are 3 electrons in this triad of 2p atomic orbitals. So does it obey the Hunds rule, and does it obey exclusion principle? Hunds rule states that these 3 electrons should fill 3 atomic orbitals before you put a second electron in. And so this electron here should not have gone in just yet. It should go in there so that you have 3 arrows all pointing up. So in this case, it's disobeying Hunds' rule. It's obeying the exclusion principle though, because none of the electrons have parallel spin within the same atomic orbital. In the second case, we see that this is the case. 2 electrons having the same spin in the 2s orbital. So it's disobeying the exclusion principle. Does it obey Hunds' rule? Yes, in this case it does. 2 electrons in the 1s, 2 electrons in the 2s, and the 4 electrons in the 2p atomic orbitals are stacked once, twice, 3 times, and then the 4th electron with anti-parallel spin goes into that 2p orbital. It's obeying Hunds' rule. In the next example, it's quite similar. The only difference is that this electron here has the same spin as its neighbour here. So Hunds' rule, once again, is being obeyed, but the exclusion principle is not. In the 4th example, we see that there are 2 electrons in the 1s orbital, only 1 electron in the 2s atomic orbital, and then 3 electrons in the 2p atomic orbital. This is actually an excited state. This example is disobeying the Aufbau Principle, which we'll discuss in a moment. In this system here, we would normally, for the ground state, put 2 electrons in this orbital, the next 2 electrons in the 2s atomic orbital, and in that case we would only have 2 electrons left. Is this example obeying Hunds Rule? Actually it is for an excited state. Is it obeying the exclusion principle? Yes, it is. No 2 electrons in the same atomic orbital have parallel spin. But it's important to note that this is an excited state, not a ground state. The Aufbau principle, which literally translates to the building up principle, describes exactly what we do when we generate these electronic configurations. That is, we place each electron in the lowest energy permittable level. And so if you look at the first example, this is for hydrogen. We see that there is 1 electron in the 1s atomic orbital. Helium has 2 valence electrons. The first one in 1s and the second electron also in 1s, but with opposite spin. Lithium has 3 valence electrons, 1, 2, and then the third must go into the 2s atomic orbital. No atomic orbital can ever be occupied by 3 electrons. 2 is the maximum number of electrons you can have in an atomic orbital. If we move on to boron, which actually has 5 valence electrons, we notice that the first 4 go in the 1s and 2s atomic orbitals. The 5th electron goes into one of the 3 2p atomic orbitals. Moving on to nitrogen, which has 7 valence electrons. Again, we put the first 4 electrons in, and then 5, 6, 7 go into the 2p atomic orbitals. Importantly, we're obeying Hunds Rule and the Pauli exclusion principle such that the electrons symmetrically go across those 3 2p atomic orbitals. Once we're in a situation where we have an 8th valence electron, such as in oxygen, put in the first 7, the 8th will traditionally go into the 2p orbital on the left. This is the 5th how-to tutorial for CHM1011. In this tutorial we're going to be looking at the different shapes and orientations of atomic orbitals. What exactly is an atomic orbital? I think this is something that is often a point of confusion for people studying chemistry for the first time. An atomic orbital is defined as a solution to the Schrödinger equation, and it's defined by quantum numbers n, the principal quantum number, L, the angular momentum quantum number, and ml, the magnetic quantum number. It's important to acknowledge and to try and grasp and understand that an orbital is a mathematical function. It's not a region of space. Okay? It's not a physical entity. It's a mathematical function which describes the probability of where you will find an electron. An orbital can exist over all space. It's not explicitly defined by some of the shapes that you'll see. For example, the radial component of a 1s orbital is 2e to the power of minus r. Okay? The solution is non-zero, no matter what value of r you choose. That is, no matter how far from the nucleus you are. This is a bit of a strange point. I mean, what I'm really saying to you is that for, take a simple example such as a hydrogen atom, there's a non-zero probability. In other words, there is some probability that the electron exists a fraction of a centimeter from the nucleus. There's also a fraction of a possibility that that electron exists a kilometer from that hydrogen atom's nucleus. The reality is that that probability is very, very small, but it is not zero. Obviously, as one's getting further and further away from the nucleus, the probability of finding that electron is smaller and smaller. So we usually describe the shape of an orbital by where an electron is likely to be found around 95% of the time. Each orbital has a unique shape with respect to the x, y, and z axes. Okay, on this slide you can see a couple of examples, and these are d orbitals. The orbitals that you should be familiar with as a part of Chem 1011 are s, p, and d orbitals. S orbitals are the simplest of these three. They have a spherical shape. The probability density changes uniformly moving away from the origin. As you can see, the radius of these s orbitals increases as you go from 1s to 2s to 3s and so on. P orbitals have what is often called a dumbbell shape, and these can have three orientations along the x, y, or z axes. And as you can see, these dumbbells are aligned along the three axes, and that's where they get their names from. So the px, in this case in the figure, the 2px atomic orbital is aligned along the x-axis. That is, it's like a shish kebab with the x-axis going through the two lobes of the dumbbell. The py atomic orbital has the y-axis going symmetrically through the dumbbell, and the pz axis has the pz orbital has the z-axis going through the dumbbell lobes. There are 5 d orbitals, and they have the shapes and orientations that you can see here. In the case of the 3dxy atomic orbital, it gets its name from the fact that it has these nodal planes. In other words, these are planes where there is zero probability of finding the electron, that runs along the zx and zy planes. Or you can say that the lobes are in the xy plane, and that's where this orbital gets its name from. In the 3dxz figure, you can see that the lobes exist in the xz plane, and you have nodal planes in the zy plane and also in the xy plane, and so on for dyz. The 3dx squared minus y squared orbital is slightly different to the first three in that the x-axis and the y-axis go symmetrically through the lobes. Finally, the 3dz squared orbital has a more odd shaped. I think of it as a dumbbell with a donut going around it, and the dumbbell is aligned along the z-axis while the donut is on the xy axis. The planes and the conical plane that you can see in that fifth example are called nodal planes. And a reminder that a nodal plane is a region where you will never ever find the electron. There is a zero probability of finding the electron in that place. Going back to the s orbitals, we can also see that there are nodal regions for the s orbitals. This is not so much in a plane, but in a spherical shape, a bit like a shell, if you like to think of it that way. Perhaps like, or the layers of an onion. Okay, in between each of those layers, where you have a non-zero probability of finding the electron, you have this shell where there is a zero probability amplitude for finding the electron. In other words, you will never find the electron there. One of the weird things about quantum chemistry is that an electron can actually go from one region through a node to the other region, but that mathematically speaking, the electron can never ever be at the spot where the node exists. There's a phenomenon called tunneling which allows the electron to go from one non-zero probability region to a neighbouring non-zero probability region. And just revising the nodal planes that we saw with both p and d atomic orbitals. Nodal plane represents a plane about which the wave function for a particular orbital has zero probability amplitude. So in the p orbital case, we can see that there is one nodal plane, and in the d orbital we can see that there are two nodal planes.